In this video, let's have a look at part B of the question. So how would the answer differ if the payoff for the dogs would be 5.5? So each would get 5.5, meaning that in this cell now we would have 5.5 and 5.5. So we'll have the same logic. We'll have a look what happens when the cats buy the goggles, the lenses, and when they don't. So let's go here below. When they buy the lenses, this would still hold, because the expected value, let's write here, part B, the expected value of the cats with the lenses would be still 6, meaning the dogs would have to interact with each other. So the expected value of the dogs would be, when the cats buy the lenses, would be 5.5. And we can see that 6 is higher than 5.5, so the cats would still be better off. Now, what would happen if instead of having lenses, we would compare the case without the lenses? Well, let's have a look. Without the lenses, the expected value of the cats would still be 6 times x. But the expected value of the dogs, would be x times the outcome of interacting with the cat is still 8 plus 1 minus x, but now the outcome of interacting with the dog is 5.5. So the math changes here a bit. We would have now 8x plus 5.5 minus 5.5x by opening the brackets. 8x minus 5.5x is equal to 2.5x plus 5.5. So the question is, which one would be higher, this one or this one? And the idea is that, would it depend at all on x? Well, let's compare 6x with the other one, and let's give an extreme case to prove a point. So if we compare over here 6x versus 2.5x plus 5.5, let's give the worst case for the dogs. Let's give the dogs 0 cats in the population so that they only interact with dogs. In that case, we would have here 0 and we would have here 5.5. Now let's give a bit of a different example. What if we give 10% of cats, so as little cats for the dogs as possible, because it's in the dog's disadvantage. It's in the dog's disadvantage to have little cats, because if they have very few cats, they have no one to dominate, so they're probably not going to be better off. But let's see what would happen. If that would be 0.1, we would have 6 times 0.1 equals to 0.6 for the cats, and if we do it for the dogs, we would have, I'm doing it on the calculator right now, 2.5 times 0.1 plus 5.5, we would have 5.75. It's ridiculously higher, 5.75, in spite of being at a disadvantage. But imagine if we actually gave a high advantage to the dogs. Let's say there would be very many cats, maybe 60%, let's say 6 times 0.6, the cats would have an expected value of 3.6, but the dogs would have 2.5 times 0.6 plus 5.5, that would be 7. Again, ridiculously higher, much higher. So the idea is this: even though the dogs are at a disadvantage having few cats, so even with few cats, dogs are better off. That's what we can see. Even at the extreme cases, from 0, from having no cats to dominate, they are better off. From having a few cats, they are better off. And obviously the pattern goes the same way, the trend goes up. Even though we have more cats, which is better for the dogs, it's obviously more likely for them to be even more better off, and that's what we see over here. So I hope this makes sense. This is more or less an intuitive question to see what happens in the worst case for the dogs, and if in the worst case for the dogs they're still better off, then obviously they're gonna always be better off, because the expected value from interacting with another dog is quite high. It's almost the same as what cats interact. So dogs are not that worse off. Like even if they don't have cats around, they're still okay interacting with each other. That's the intuition of the question. Hope this makes sense, and we are done.